so much, Nathaniel. So the next portion of our day is going to be a presentation by Omid. He's a sophomore computer science and math major and also one of our curriculum directors.
Yeah, and the presentation is called Hello World Coding, Coding Fundamentals and How to Teach Them. And we'll have Omid up here.
Technical difficulties, sorry.
Thank you.
All right, hi everyone. My name is Omid. I'm a sophomore here at Yale. I'm studying math and computer science, trying to double major here, and I'm also one of the curriculum directors of Codehaven, along with Claire, whom you met earlier. So the point of this talk today, Hello World, Coding Fundamentals and How to Teach Them. The idea here is not really to teach any of you about teaching, because honestly, I could probably learn a lot from all of you about teaching specifically. So what I'm going to focus on today is two very specific questions where I think I could be most helpful. So the first of those questions is, number one, what are the big idea fundamentals of CS? And what I mean by this are, what are the vocab words? What are the key terms, the key constructs that you see in code that occur over and over again? So we're going to go over what all of those are, and spoiler alert, there aren't that many to worry about. There's not a huge knowledge barrier to start working in CS. And question two is, given those fundamentals that we're going to go over, how do you implement those in terms of the classroom? So basically the focus of this talk is going to be much more on the nitty-gritty of how you can implement specific activities and how you can plan lesson plans that center around CS. And this is kind of based on the experience that Claire and I have on creating lessons for Codehaven. So these are 1 hour lessons that we go in once a week into these classrooms and try to basically structure it so that we get the maximum impact in each of those hours every week. So just a brief outline of what we're going to be going over. First, I'm just going to talk briefly about what makes Codehaven a bit unique, a bit of our teaching philosophy. Then we're going to go into question one about CS fundamentals. We're going to move into the second part about classroom integration. I'm going to show you guys an example of actual lesson plan that we would use in a classroom. And then we're just going to, the fun part of this will just be, we're going to go after one activity after another, showing you guys what we would actually do in a classroom to teach a concept like loops, for example. And throughout, I'm going to be asking for questions. I really want this to be as helpful as possible for all of you. So if there's something that I'm not addressing, please let me know, and I'll do my best to address it. Okay, so a bit about Codehaven in particular. Just a couple points about stuff that we emphasize. Number one, we think that students learn much more through doing an activity than through listening in a lecture, specifically with regards to coding. So what this means for us is we try to minimize the amount of time that we have a mentor or a teacher standing in front of a classroom and lecturing, kind of like I am now. We don't want this to be what a classroom looks like. Much more, we'd rather prefer most of the time to be students actually sitting at computers, working on code with each other or on their own, with mentors' help, or doing an activity that's related to code. We feel like all of that time where they're actually struggling and working through problems and learning things on their own through experience is much more useful for CS than us just feeding them knowledge in a lecture. So that's point one. Number two, gamify your lessons. Make them as fun as possible. So we really make an effort when we plan our curriculum to make learning as little of a chore as we can. So obviously computer science can be very daunting. We want it to be as fun as possible. I mean, if you were just listening to Nathaniel's talk right before me, you could just see how easy it is. Not how easy it is, But if you have someone put in the effort to make computer science accessible and like extract out the interesting parts and really unpack concepts, then there's a lot of fun stuff for that's extremely accessible. So you want to put in that effort to gamify your lessons. Number 3, the work should have tangible rewards. An example of this is we have this program that you're going to learn about called App Inventor, which is this environment for coding where kids drag and drop these blocks onto a screen, and they can scan things with Android phones. They can scan the code on the computer, and on their phone they'll get a version of the app they built. And we think that's really cool because it's basically, once you spend like 45 minutes working on this coding project, or maybe it's like a multi-week project that you invested a lot of time into, having a physical like a rendition of it on a phone or like on a website on a computer is kind of like a proof of concept to these kids. Like, wow, I put in all this time and I actually built something at the end. Like, here's something I can show to my friends. Here's something I can go home and show my parents that I'm doing, and it's creating something of value. This is really important too because, as Nathaniel mentioned, like not everyone that does. Go ahead.
Excuse me. I'm doing that for the first time.
The app event?
Yeah, at Hill House.
Oh, perfect.
Yeah, I'm teaching.
Okay, great. Yeah, we're gonna talk a lot about App Inventor. Like, it's a really great program. So like, yeah, a part of the reason that we like to focus on the on things like that where you actually have like the end product is because like not everyone's going to be a software engineer, not everyone's going to go to the academics of computer science, and to show why it's really accessible, I think it's really important to prove to kids you can build a product in a reasonable amount of time that is useful to people. So having these tangible rewards is essential to convincing kids that computer science is useful. And this is something very specific to Codehaven, but I just want to mention that in our classrooms, we have a ratio of like 1 mentor to 4 to 5 students. This isn't like feasible in every single sort of classroom. This is kind of something unique to Codehaven. But in general, trying to increase the one-on-one time that you get with students as much as you can, we found is super valuable. Any questions so far? Yeah.
Just for folks who are going like, man, yeah, that would be great. But where do I get 5 extra instructors in my classroom? One great answer to that is your students. So you can noodle on that for a few minutes, but are there students available to you who would become those mentors for other students?
That's a good point. Any more questions?
In terms of the rewards and equity, if you're in a school that students don't have iPhones or tablets or even computers at home, how does that work?
That's a good point. You don't all like when I say tangible rewards. I guess like that's a little misleading because it might not be something that's like a reward that you have to buy. It's in a sense what I mean by that is like when you basically the work that you go towards, assuming that you have a base of like a laptop, which is kind of like a prerequisite, and that's like a whole issue of equity on its own. But like if you have even a laptop, if you have a final product that is something cool, like something like you're working on Code.org, for example, and you make some project on Code.org, or you're working on App Inventor, and you're able to make this app on the computer, like not necessarily on a phone, that is like does something cool. Like maybe when you type in something, it says what you type in, or maybe like when you'll make a homepage for yourself, like a website for yourself. Things that are, I guess, useful, like was kind of what I mean by tangible rewards, like a project that you can show to people and be proud of. And I guess there is the question of equity, like do we have the technologies to give people these awards? But I think that's less relevant. And just being as long as you have a laptop for students, then you already have the prerequisites to make things that are of value.
I think one other thing, just jumping on that, just because I'm teaching the unplugged activities thing, because I'm like pitching myself. But also, if you don't, we do have activities that we do without computers too. They're called unplugged activities, and it's like computer science without needing like technology that costs money. So we'll have a workshop on that as well later too.
Well, another thought about these things in general is badges, and kids can earn these badges, and then they, collect them. So it's sort of like, you collect Pokemon cards, and maybe you can have the skill set, and then you have that identification on your, even your Google, depending on what you have on your computer to get to school. So badging is another way of providing that done something for y'all.
Yeah, and that's a really good point. Like if you go to platforms online like Khan Academy, they have stuff like badges for your profile. Like if you complete a certain number of exercises, then you get these badges. That ties into the point again about gamifying learning. Like it becomes a game of how many points can I get on my account by doing these exercises, rather than how much like CS can I learn. And that also ties into another point that I'm going to get into later. But most of the work has been done for us. Like there are people investing a lot of time and money into creating the most like easy ways for students to learn computer science. So things like Khan Academy App Inventor are extremely like useful to know that those exist. Okay, in interest of time, we're going to move on. So we're going to talk about the actual fundamentals I alluded to earlier. So the 5 that we're going to talk about, and are probably the only ones you need to worry about for most Intro CS classes, are 1, algorithms, 2, loops, 3, conditionals, 4, variables, 5, functions, or abstraction. And we're going to go into all these in a little bit more detail. And you probably are familiar with several of these terms, or probably all of these terms, if you, like not even in a CS context, but like in math or in just like everyday, like everyone knows the word like loops, for example. And so we're going to talk about them in a CS context and just recognize that there aren't a lot of words that we need to know. There's not a huge knowledge barrier to CS. And these are all on the worksheet too that I think you all got. So in addition to talking about fundamentals, I want to mention the idea of programmatic thinking. I'm going to confess, I don't think this is an actual term. I think what Nathaniel used about computational thinking is like the real term. But basically, so like on the slide is a lot of information, but the idea is that, right, so we're going to talk about the fundamentals, but those aren't like the core hurdle that your students are going to have when learning computer science. The core hurdle is the attitude and the mindset that you have when you approach problems. So just going, like reading what we have on the slide, break the problem into smaller pieces. If you have a huge like app that you want to build that, I don't know, maybe organizes your classes or something like that, that's a lot of steps. Like you can't like just jump into that. And it's pretty intimidating if you haven't tried something like that before. So the idea of trying to break things into smaller pieces, the idea of debugging or making small changes. So like say your code doesn't work. Like what do? You have to, you can't like just like stare at the code and kind of wait for the revelation to come to you. Like we try to emphasize, and you can't, this is something that you can't really teach, what students have to realize themselves. You have to just start, you have to try and realize where the problem is and make changes rather than staring at code, which is like easier said than done. It's very easy to get frustrated with code that doesn't work. And the third point here is perseverance. This is something that I like continually find in my classes like here at Yale. But CS is very unforgiving. Like you can have tests that you want your code to pass. Like for example, is this returning the number that I want? And it doesn't work. And the computer doesn't tell you why, because the computer doesn't know why. And then you don't know why. So like it's like I put all this effort in and my code isn't working and I don't know why. And it's sometimes hard for other people to help you because maybe you put so much work into your code base. People don't understand. People aren't familiar with it, so it's a skill of perseverance to be able to go back into your code base and figure out what's wrong. Like it requires a lot of like emotional perseverance, and it's an iterative process. Like you have to keep like finding out what's wrong and trying to work based on that. So I just want to break down like what kind of stuff our syllabus covers, so you have a kind of a sense of what we're mostly doing in these classes. Our class is 15 weeks, so these are all 1-hour sessions. And by the end of this class, you have students on App Inventor like making their own apps independently, like the last 4 weeks of our project. But the main thing I want to point out is that if you look at the key on the right, you have yellow algorithms, blue conditionals, green variables. The top 3, the algorithms, conditions, and variables, are the actual like concepts that you are teaching explicitly. And those are only 4 out of the 15 lessons that we're teaching. So like 4 out of 15, that's not a lot. The rest of these are just projects that we assign, and for most of these class periods, the students are just set on their own or in pairs with their mentors, and they're working on these projects on their own. They're struggling, they're running into bugs, they're trying to fix what goes wrong, and this goes back to like how we believe that's the most effective way for these students to learn. We make this, that's why we have so much project and building in our classes, versus versus a lot of teaching. Any questions before I go on to the next section? Awesome. So how do the bread and butter? How do you actually teach these things in a classroom? So I'm going to show you guys an example of a lesson plan that we would actually use, just so you know how we break down the 1 hour that we have. It's a little small. So this is for an app that we do in our second week of classes called Hello Purr. It's literally like a cat on a screen, and you tap the cat and it makes a purring noise. Pretty simple, but like it's pretty satisfying for these kids for the first time to make their app, and when they touch it, it like responds to them. It's a physical response. So the first 5 minutes would just be like we're coming into a classroom. Hi, how are you? How was your week? Like, would you remember what we did last week? For minute 5 to minute 30, we are splitting into our mentor groups. So one mentor per 4 or 5 students, and they just have at the problem. Like maybe we'll give them a worksheet that explains what the code, what their assignment is. But other than that, they're basically set on their own, and are struggling with problems, asking questions when they run into problems. At minute like 30 to 35, we'll say, all right, everyone check in up at the front of the class, raise hands for like what questions you have, like what's hard, how far are you, just so that they're not completely set on their own, so that they know that where other people are and where they can get help from. And then at the end, we just continue basically for the rest of the class to continue coding. You'll find that a lot of students like breeze through these exercises, like a lot of students that are comfortable with computers or are good with math, or maybe have had experience with this type of thing before, will breeze through your exercises and finish them quickly, whereas others will like need a lot more time. So there's a lot of ways you could address that. There's like having the students that finish quickly help the students that are not finished yet. What we do a lot is we come up with extra exercises to keep those kids occupied that finish early. Like for example, okay, you made your Hello Purr app, and when you click on the cat, it makes a purr noise. Can you, on your own, find a picture of a dog, put a dog button on your app, and then make it do a dog noise? Like, just, they're easy to think of, but they are challenges for the kids to do, and they also, so that they're making the most of their time. One more thing that we often do is we have these things called maker cards. The curriculum that we use from CS and SF, we'll talk about that later, but these are cards, each of which has some sort of task. Like, so you could maybe have a physical deck in your classroom, and they say, okay, you're done with your work, take a maker card. Let's say they do number 3. We've actually done this one in class. Make your phone speak to you. Type a phrase in a text box. Then press a button and use the text-to-speech component to let the phone speak the text that was typed. So like when our kids finish early, we'd say, take this maker card and just build this. Like no other instructions, you know what to do. Just go ahead and try and see if you can make this product. And having this sort of, and this is something that like kids find extremely fun, because like it's something that you can customize, you can type in whatever you want. A lot of kids just like will have at it with the curse words, so you have to kind of put a censor on that. But it tends to be just the idea of having these things that can keep these kids these challenges in case people finish early. Alright, so now we're going to get into actual activities that we do. So the first one is based on algorithms. An algorithm, as you probably know, is a list of steps that you can follow to finish a task. So the activity that we use for algorithms in classrooms is this gift wrapping challenge. You might have seen a variation of it before. Basically what we do is we have 2 robots. 3 robots. Okay, so I guess you guys can come up here where it's visible. We have a box, and we have some wrapping paper, and we have tape. And what we have students, or in this case you guys do, is everyone gives one instruction at a time. The goal is to instruct these robots, who are computers, who have no like prior knowledge of it, like except for basic English, but have no knowledge of the world or of wrapping presents. You have to tell them exactly how to wrap this gift. And again, the materials we have are a box and a lid, wrapping paper, a bow, tape, and scissors. So if I can get like volunteers, like one at a time, just shout out an instruction, like how should we wrap this present?
Unfold wrapping paper.
Okay, unfold wrapping paper.
Put
Okay.
the top on the box.
Put the top on the box. Okay, so that didn't go as planned. Yes?
You have to take the top and fit it to close the box. Flip
What's
flip
close?
the top over.
What does close mean?
Can people over there see?
Really?
Okay, we got turn the lid.
Degrees.
Rotate the lid
Might have any degrees.
by 90 degrees.
Pick up off floor.
Alright, let's keep going. I think we can get this. So it's kind of
Make
on.
sure
Yes.
the lid fits evenly around the rectangular shape.
Make sure the lid fits evenly around the rectangular shape.
You were on top. Why did you move the?
Don't yell.
So these are not smart robots.
So we'll jump to avocado box.
Okay. So okay, we got a little bit of a cheat there,
Okay.
but we'll keep going. So how do you wrap the present? Yes.
Take box with lid, put in center of wrapping paper.
Okay. Any more?
Place it flat on the table.
Place it flat on the table. We're like halfway there.
Fold side of paper up.
Fold side of paper up.
And tape end to the box.
Tape end to the box. So they don't know what tape means.
Take half an inch of tape off with the dispenser.
Take half an inch of tape off of the dispenser. And then what?
Take half an inch of tape to the paper, to the edge of the.
I'm gonna try a big one. Repeat 3 times. Repeat function 3 times, rotating your body 90 degrees.
Rotating
Rotating
the box.
box,
90
90.
Rotating the box 90 degrees.
And the paper.
Something like that. There's a place for a loop.
There's a place for
I guess what are you gonna put? Which function or which actions are you on inside? Are you?
Tape
So
paper
okay, so
from
you
table.
said
Someone want to amend it? This is why we do pair programming. We need help from buddies. No.
Do you have any more advice? We're looks like we're 3/4 of the way to 1/4 of the way to wrapping this. Yeah.
So let's put that repeat statement around the part where we folded the paper up, but each time rotate the box with paper 90 degrees.
The smart student.
I'd wrap presents in my day.
Yes.
Put an instruction in to make sure that paper fits snugly to box because you're pulling it over, but it's not.
That's like the way it moved.
Yeah. If you could say something like
So make sure the paper wraps snugly to the box.
to the box, and
Okay.
then apply tape and hold in place, hold paper in place.
I'll give a reference for this.
We'll try a few more instructions. So we're fitting it snugly.
Snugly. Snugly to find down.
It looks like my wrap.
One last step.
Please turn the box over.
You got more than one last
Remove sticker.
Okay. Well done. Okay, so that's about how far our students usually get. So give yourselves a round of applause. That was awesome. It takes a lot longer.
That's better than my kids did.
Okay. Okay, thank you guys for doing that. I know. So this is we love doing this activity. Just a reflection on that. Students get very highly engaged with this activity. as I noticed, like a lot of you it's very easy to get frustrated with these robots because you're clearly, you know in your mind exactly what you want these robots to do. Like you can picture yourself, you want to just go and physically do what they're doing. But the problem is, you can't. The robots have to do it. And the fact that they're not doing what you're doing really frustrates you. A lot of times in classes, you just see like kids physically like kind of like, oh my gosh, this is crazy. Like I know what this is supposed to do. So what this really effectively demonstrates for these kids is that the robots are not on your side. They're not against you either, but they're completely neutral. Like they don't have any relation to you. They're just like doing what you tell them exactly. So
worst comes to worst, can we just kick the robots?
Yeah, but then you have to buy new computers. So this is usually very effective for demonstrating like firsthand like how hard it is to tell a computer exactly what to do and why your algorithms have to be very effective. And just a few common pitfalls that you notice when you do this demo. You typically get a few kids, like usually the ones that are answering all your questions all the time, but they're the ones who want to like basically give you the entire algorithm. So like, even though like it was like physically uncomfortable for me to like wait for like new people to raise hands, but that's just typically, it works well because the longer you wait, like you get more kids getting just frustrated, like I don't want to wait, like I want this to be done, so I'm just gonna raise my hand and like give an instruction. So it's really effective for that. And sometimes you notice that like people have different ideas of what the end present should look like. Like maybe one wants to put like the bow on the other side or like have it shaped differently, I don't know. But that's also another, like, actually maybe that's a teaching point because you can point out that you can do this algorithm in different ways. But really effective in general activity. We really love doing this for algorithms. All right, next one. So the next concept is loops. And the loop is just the action of doing something over and over again. Simple enough, right? I'm going to show you guys an example of what loops look like in actual code. Is that there's this variable called I. And initially it's going to be 0. And then so when I is 0, you're going to print the number 0. So basically, the output of this program is the number 0. And then it's going to go back and do it again, except I is now 1. So then you're going to print 1. And then you're going to go back again until it's 2. And it's going to go back again. You're going to keep going and printing I like 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 9. It won't do 10 because that's how Python works. But that's basically the idea of a loop. You're just doing something over and over again. An alternative way to do this would be to literally say print 0, print 1, print 2, all the way up to print 9. But obviously that would be a lot harder. Like you'd have to copy and paste and like change everything. So loops are really are used like paramount to basically to writing code. And another example on the right is what a loop looks like in Codeorg. So all our students, like we don't actually show them the code on the left. We don't show them Python code. For a number of reasons, like we just don't have time for it in our time span, and because like we think that the right actually captures the concept a lot more. But let me show you. If you haven't seen Code.org, this might be a bit confusing, so I'm going to go ahead. But basically, what Code.org does is like you're in this environment. These are Angry Birds. If you guys have ever played that game. Basically, the goal is to get this red bird to this green monster or whatever it is. So one thing you could say is just keep moving forward. So how many spaces is that? 1, 2, 3, 4, 5. So you could tell the red bird to move forward 5 times when you click run. So 1, 2, 3, 4, 5. Right, so that's one way to do it. Let's run it and see how. Kids love this because they love Angry Birds. Okay, so that worked, right? We got to the end. But that's not the point of this activity. The point of this activity is to use a loop. So instead of like dragging move forward out 5 times, what we could just do is say repeat until we get to the green monster. What do we want to repeat? We want to repeat move forward. And we didn't even have to tell it how many times to do it. Let's see what happened.
And in Python, what would that look like?
In Python, what this would look, oh, the birds?
No, I mean like, repeat, you're not giving it a defined range, right? The range is that until you hit a...
Yeah, an example of that is like if you use a while loop in Python. If you've done coding, you know what a while loop is. If not, we don't need to go into it now, but basically it's another way of doing a loop without telling it explicitly, I want to do it 10 times. You could say, just keep doing this until something happens, like until I reach the bird. or until I equals like 20 or something like that.
And Code even does have a button that says show code, right? That kids
Codeorg,
can
yes.
press.
That's a good point. In Codeorg, if the kids want to see what the code looks like in JavaScript or whatever language it is, they can actually see it. Usually they don't want to,
Yeah.
so we usually don't show them that, but it's important to point out.
Scratch does not have that though, right?
As far as I know, Scratch does not. Scratch, for those of you that don't know, it's similar to Code.org. They have blocks to do code. Okay, so this is what we do for loops usually. We do something called the loop dance. We took this from Code.org. They have a name for it. It's called the iteration, which, yeah, I don't like the name. But basically, how the dance works is that each of these boxes is a dance move that you do in time. So you would go clap, 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 behind head, waist, behind head, waist. So this is a dance. So I'm just like, let's demo the dance. My helpers are gonna help me out. They're gonna do a dance. We're just gonna. It's important to mention also on the left, I have written all of them, all the instructions out in words. So I'm just gonna read them out, and they're gonna do them, and we're gonna see what the dance looks like. There's this
also,
part.
if you'd like to dance with us, we would love to help. We know you've been sitting for a while, so this might be a good chance to get blood moving.
Yeah.
Also, we won't be doing this by ourselves.
Okay. So we're also this part that says repeat 3 times. We're just gonna ignore that and go to the belly laugh. But let's do this. All right. 1, 2, 3, 4. Clap, clap, clap. Behind head, waist. Behind head, waist. Clap, clap, clap. Left up, right up. Left up, right up. Clap, clap, clap. Belly laugh. Okay, so that's usually fun. Like kids get like, because they're like, oh, this is cool. We're doing stuff. Okay, so that's step 1. Step 2 is the loop part. So as you notice, we did a lot of things more than once. Like we clapped 3 times. I shouldn't have had to say clap, clap, clap. Like I could have conveyed the same information by saying clap 3 times. So how we do this in a classroom is that this worksheet that you see on the screen, we would hand out to the students on a piece of paper, and they would cross out all the redundancies. What that means is that like as you see like clap appears 3 times, you circle the first one, write the number 3, and then cross out the other 2. And then, so you do that throughout the entire sheet. So, so for example, if you look at the screen, what's the next example of a repetition? Can anyone point out to me like what that is?
Right there.
Exactly. Behind head waist is repeated, which is a good point. Like a lot of students don't realize that you can repeat more than one thing. So behind head and waist are one chunk that you repeat again. Then you have clap, clap, clap again. Then you have. Oh, I should be writing these down. Hold on. So yeah, as the students like tell us, we would like write the numbers. So behind head waist, as we pointed out, is 2 times. So I'll put them in parentheses just to show that this is one thing that we did twice. And then what's the next one?
Clap 3 times.
Clap 3 times. How about the next one?
Left up, right up.
Yeah, left up, right up is repeated. So I'll put those in parentheses. That's
never
repeated.
said left down though. So when we were doing this, I had my left hand up the whole time.
That's a good point. That's actually a very legitimate point. Like that's a flaw in this program.
It was a sin.
Okay, what's the next repetition?
Clap 3 times.
Right, so that's the last one.
And then of course, all of this would be in a repeat function 3 times if we follow the original instructions.
Exactly. Yeah. So if we want to actually follow the instructions, all this would be in one like giant parentheses, and we put times 3 before we put the belly line. So let's do it one more time.
Fourth belly.
If you guys would like to indulge me, like we'll do this one more time, and instead of saying clap, 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 I'll just say clap 3 times. So let's do it one more time. So 1, 2, 3, 4. Clap 3 times. Behind head waist twice. Clap 3 times. Left up, right up twice. Clap 3 times. And then belly laugh. Okay, thank you guys so much. You results are okay, so that one's really fun because like, yeah, obviously your kids are going to be doing stuff, and it's going to be like physical. If you're a kinesthetic learner, you easily just get comfortable, like you explore the space around you. It's usually like after the first like couple claps, like kids, it's not awkward anymore. And it really like physically unpacks this concept of loops. Like if you tell kids like loops are repeating things like over and over, like okay, like thank you for telling me. But like if you unpack the concept, like it physically like there's like a it internalizes it. Common pitfalls, the usual ones that we see is that like students don't realize that you can have more than one thing inside the loop. So you guys like pointed out immediately, but the behind, head, and waist, that the fact that you can have those be in one loop that you repeat is for a lot of people not immediately obvious. There's also the thing that the entire thing is supposed to be repeated 3 times, but like that's a lot of dancing. So that's a good one. So we'll skip that video. We have one more activity with conditionals. I won't make you guys dance again. Like we'll have our helpers do it, unless you want to. Like you're more than happy. But basically, what conditionals are, a bit of an explanation, are just statements that only run under certain conditions. So for example, if I'm at a traffic light, if the light is red, then I will stop my car. If the light is yellow, then I will slow down. If the light is green, then I will keep going. And so that's basically what a conditional is. Under certain conditions, you respond in different ways. And under certain conditions, your program will respond in different ways. Again, this is just an example with Python. On the left, so I'll explain this briefly. Basically, we're saying that the variable x is 5. If x is less than 0, which we already know it's not, but like the program doesn't know that. If x is less than 0, then we're going to say x is negative. If x is greater than 0, we're going to say it's positive. Else, which means in every other case, we're going to say 0. So either you're negative, positive, or 0. And in Codeorg, this is just a path where if there's a path to the right, you're going to turn right. Our activity for this is basically another dance based on colors. So what we're going to have is just basically a conditional a body of conditional statements. So if the color on the screen is orange, put your hands on your shoulders. If the color is green, clap your hands twice. If the color is blue, hands on your hips. If the color is purple, stamp your feet. And in all other cases, hands on your head. And it's important to keep in mind that else statement. That's something that's not always obvious. But the else basically means if none of the other cases are satisfied, then you go to the else statement. So we're going to go ahead and try this dance. So first, climb. That's blue. That's right, so that's an else.
Sorry.
That's blue.
Okay, faster.
Right, okay, you guys got it. That's not purple. That is pink. So that is hands on your head. Okay, so common pitfalls of that, like, I mean, it's cool because of the same reasons, like it's physical and like it's something that like is a break from like lecture. Common pitfalls is that like as I noticed as I went a little faster, like there's obviously like kids are going to be like more pressure to come with the right answer, and they'll like kind of assume they know what it is, but not go through the entire like if statement and check all the conditions. A really common pitfall that's like really important in if-else statements is the else block. Like it's easy to think that conditionals are just if, and in a sense they kind of are, but you have to think about the else block, which means that if none of the previous conditions are satisfied, this is what you do, which is extremely useful when you're writing conditional statements. The next two concepts I'm not going to go over very much because they're variable and function. I'll tell what they are in their programming context. But in reality, in the programs that we use in Codeorg and in App Inventor, variables and functions are kind of implicit in the actual format of the environment, which is kind of hard to show without. I'll show you as an example. What a variable is a placeholder for a piece of information that can change. Very similar to a variable in math. So like in a previous example for conditionals, we had x equals 5. X is a variable. There are some subtleties when you write code about how you assign variables and how you compare variables. But for usually for an intro CS class, you usually don't get into the nitty-gritty of that. And usually Codeorg kind of like delays the need to know what a variable is. I guess is a good way to put it. Another example is function, which is a pretty high-level concept and very important to learn. We typically don't get to it in our lesson, in our 15-week like lessons. And what that is a piece of code that you can easily call over and over again. So, for example, like when we were wrapping this present, a function that Dave was trying to implement was basically tape up one side, which consisted of like taping up, folding up one side of the paper over the box snugly, and taping the tape onto that from the paper onto the box. So all of that is a repeated thing that you would do, and you give a name to it, like call it like tape up or tape side or something like that. That's a function, which is indicative of a concept called abstraction, which Nathaniel went into depth about. Very important, but we just typically don't get into it, so I'm just not gonna go over a specific example. Okay, and then the last example I have is an actual coding example. So all those were more like what we call unplugged activities, so like physical things that you do to teach these concepts. Here's an example of an activity that we would have students. Okay, I'm gonna switch accounts real quick. Basically, I'm just pulling up the activity that we're going to be using.
Oh, one other thing I will add to Omid's thoughts so far, another teaching tool that we use a lot of the time is after we've done an abstract activity like this, where we give an example such as dancing or traffic lights for conditionals, that's very real world and about the students. Sometimes it's a little bit difficult for them to bring a metaphorical explanation into their actual projects with code, so typically we accompany activities like this with a worksheet that explains how to implement what we're talking about with the actual coding platform that they're using. So to show them, for instance, in Codeorg, which blocks are the conditional blocks, and what does this mean in terms of what I'm actually trying to accomplish in my code. And then to give them coding steps in order to walk them through exactly what they're doing. Because I guess debugging and learning the coding interface is not the chief thing that we want them to be focusing on. It's much more about understanding the concepts and implementing those. I saw some questions, yeah.
The target audience for this is 6, 7, 8, or 8, or where are you?
Typically we focus around 6th, but we have a pretty wide range of classrooms. Some of them have multiple ages, but middle school, typically early middle school is where
Okay, and it's 15 a week?
Yes. Yeah.
So this is pretty general, so you could feel free to defer to this, but have you done any measurement on, say, a drop-off of attendance or interest where by week 7 or 9, a certain percentage of the students have clearly disconnected? Do we have any measurement there? And the second thing is, are you seeing that the learning acceptance of what you're doing, is it a continuously upward moving curve, or do you find that the learning has a plateau and it stays at a plateau type of level? I'm wondering what your real world, maybe our teacher expert wants to jump in on that, I don't know.
My answer might be too optimistic given the nature of your question. I mean, I'm seeing, especially with my English language learners, like I'm seeing as vocabulary develops.
Right.
And both, I mean, like English vocabulary, but also like digital vocabulary.
Yeah.
And App Inventor is a great example because we're through 7-8 weeks or so of curriculum. things get more things seem to get more fun as students have a better sense of like how programs work. Codeorg was an easier it was easier for us to get to a fun place because it's super gamified learning. This is App Inventor requires a little bit more patience because it's super cool that kids get to put things on a phone and their app works and that's fun, but like this requires a lot of on-ramping, I think, before kids can start to feel excited about what's going on, if I'm being honest.
Can I follow up with that? I'm in a non-ESL 7th grade classroom at Mission Woods, and so we've been using App Inventor the whole semester. And so my kids actually found it was kind of the opposite. Instead of a drop-off, it's kind of been like a U-curve. At the beginning, they showed up and they were really, really psyched. And they were like, hey, this is cool, this is new, this is fun. And the apps were really easy at the beginning. And then they got, as they started getting harder, the kids started, like if there was a little bit lack of engagement or there were kids that were like, wait, this is hard, I actually have to think about this. This isn't just like fun play with a phone. Why am I here? And then we have, as the apps, as they've learned more and as they've gotten more familiar with the software, like I actually just felt that turning point 2 weeks ago when it went from, like, there were kids that, you always had to pull along and you could see just, it was, I don't know, I was not expecting it to be that sharp, but I just walked into the classroom at the end of a lesson. It just felt like all of a sudden, most of my kids were engaged. They figured out how to find stuff in the user interface. They were able to navigate it, and they were able to see that these apps that they can build are really cool. They can do really cool things. And we do survey our kids every week. We ask them a couple quick questions, like if we're doing the conditionals thing, like, okay, like what was your takeaway about conditionals? Which words would you see in a conditional? Which of these is a real life example of a conditional? And we also ask them to rate the lesson, how they thought the mentors did, how engaged they were. So we do collect info from each week how the kids do. And I think it has been, like, it definitely is, like Dave said, it is a lot to pick up, but it is something that they don't drop off. They do come through the other side and are really excited about it. I'll just back that up also concretely with survey data where we ask for, do you like lesson A more than lesson B, lesson B more than lesson C, and it's pretty much they rank it like this way. So they're actually like, I don't know, it's like kid ranking, so it's not maybe how they like felt at the moment, but definitely they're increasing engagement over time.
I will take more questions. I'm just going to point out like one other example of that. Part of like the reason that we have like this like U-curve thing that Alice talked about is when we were using App Inventor, like this is App Inventor on the screen by the way. A very like annoying part about App Inventor is just not knowing where the parts are. So what this does is this is an app where this is like Microsoft Paint. The colors at the top are the color you're drawing with, and then like this shows up on your phone, and when you click the color, like you click red, you can draw on the cat in red. So like a challenge that comes up a lot is, for example, you have to put in something called a canvas component, which is something that you can paint on, and then the kids are like, okay, like I don't know this program, where's the canvas component? And this kind of just like you can't. I mean, you can either, there's two options. You can either let them like look around this entire program, click a bunch of buttons to find it, which isn't really instructive for them about computer science. Or sometimes you just have to tell them like, oh, go to the drawing and animation thing on the left and and drag a canvas onto the screen. Which is kind of like not that fun. You're dragging and dropping things without like immediate like rewards for that. So that's just part of the example that why it's initially covered. Yeah.
I went through the program with Trinity College and at Southern by way of MIT, and they are taking research from it. And we had a pre-
At Trinity?
Yes, yeah. Pre-survey. We have tests that they have.
Because with all the teachers, no one should necessarily have an expectation that at the end of time certain, whenever the measurement of time would be, that you're going to have 92.5% high achievement rate. Otherwise, I mean, there needs to be a realistic expectation as to what the outcome is likely to be. And then that way the teacher can adjust their normative expectations, or otherwise the teacher's going to feel like they haven't made a connection. Does that make any sense?
Yes. Well, the MIT, Trinity, they are collecting.
They are doing that measurement.
Yeah, I signed up with my principal. All my kids signed a paper. They know that their parents know that they're getting information from us.
Thank you so much.
We can probably also take, yeah.
Yeah, I just wanted couple of thoughts reflecting on the discussion a little bit. Actually, can you put App Inventor back up for a sec?
Yeah.
So this gets to something I love when I'm working with teachers. You've all experienced this game that sometimes you're playing in your classroom called Guess What's on the Teacher's Mind? Like sometimes you'll notice, oh shoot, I'm accidentally playing Guess What's on the Teacher's Mind with my students, right? And like this is what Omid was talking about. Like whenever you're using a piece of technology that the students have to interact with, you have to decide to what extent do the students need to construct their own understanding, and to what extent should I be giving them an understanding?
Correct.
And so as Omid was saying, finding where the button is to do the thing that they need to do, that's not learning. Right? Like, yeah, it's learning, but that's not our learning objective. That's not the thing we're trying to learn about today. We could spend 10 minutes with them hunting around this complicated interface to find that button. It's kind of similar to when I ask a question that has one very distinct answer that I want, but it's not a math problem. It's just, hey, I want you to describe this book you just read and use the exact word that I thought of. Well, that's guess what's on the teacher's mind. This is guess where the user interface is located, and it's not going to be a very conducive way. And that comes up a lot whenever you're going to use technology in a classroom. On the research front, I think there's not an easy answer to your question. It's going to vary, of course, by what curriculum you're using, but it's also going to vary about the students in your room. No, I think you're right. We shouldn't have unreasonable expectations about any particular subject or lesson or course. You know, this isn't a panacea. This isn't going to solve all of education. It's just a really cool subject that's going to help students learn important things. That said, we do generally see higher levels of engagement with any kind of project-based learning.
Hands-on learning.
Yeah.
Right, and computer science is a domain where it's much easier to, right, it's actively hard to study this stuff without being hands-on and without using projects. So in general, we see higher engagement across a wide range of age levels and curriculum.
Okay, thank you, Nathan. That's a lot of good points. That's actually all for me. So hopefully that was helpful. Hopefully you guys got a better sense of like how we do curriculum in Codehaven. I'm going to defer to the rest of our board to introduce the workshops that we'll be having. But thank you guys for listening. Hope that was helpful.
Can I ask a question before we move on?
Oh, sure.
You switched from Code.org to MIT App Inventor, and I'd kind of like to know why and...
Yeah, that's fair. Like MIT App Inventor, I'll just show you real quick before we move on. MIT App Inventor is like the one page that I didn't show you on App Inventor is this block page. So they have very similar blocks. A lot of this interface about blocks, this is also similar to Scratch, which is a similar technology that has these block coding. The reason I switched was just because I thought like in that specific example it'd be quicker to show you guys the Code.org example of like a bird going to a monster than like...
Actually, it was like with our students.
Oh, with our students. Oh, I'm sorry. You can...
So I think so with our students we found Code.org is a lot simpler for beginner coders because there's a lot more abstracted out, but we started finding that some of the concepts we wanted to talk about were harder to find in Code.org. And also App Inventor is something like it's a lot easier to create projects with, or so part of the thing that this year, since this is our second year, we now get our kids for a full year. So we wanted to be able to work towards some project at the end, and that's a lot easier to do with App Inventor than what Codeorg lets us do.
And as a practitioner, I would simply say, App Inventor is a great thing to do when you have an extra 6 adults in the room. And Code.org is a thing that doesn't even require like a login that you can have kids do in any free block of time that you have. It's a super gamified thing. So you can do both.
And it depends on the classroom. For instance, I am in a classroom where we considered doing App Inventor but ultimately stayed with Code.org because of the culture of that classroom and the number of students versus mentors that we were working with. And that's been doing a lot better for us. And part of that, I think, is the learning arc of Code.org. So learning the interface of that website is much simpler than App Inventor, and the number of computer science concepts that you have to understand in order to make something or to accomplish something is much smaller. So you do these small puzzles like Omid has showed us. It's very gamified, as Dave said. So the arc from beginning a puzzle to gratification and reward is very short. and you can do one and feel like you've accomplished something, whereas App Inventor is a much longer arc in that respect. So as we said, the onboarding process for that is longer, and then also it takes longer to have accomplished something. However, that thing can be larger. So that is, I'm sure, a dynamic that you balance in all areas of your teaching. It's a pretty fundamental thing, but hopefully the workshops also will be helpful with this, because different tools for teaching computer science have different characteristics in those respects and work better for different classrooms. Yeah.
You mentioned Code.org. I had my kids do that a little bit, and it was under Hour of Code.
Yeah.
Okay, that specifically under that, because it looked like Code.org was a whole encyclopedia,
Oh,
and
yeah,
that was
so
bringing out
Code.org
one book. So it's Hour
Code.org
of Code.
Yeah, Codeorg is this like big company that basically focuses on CS education. They have a lot of programs.
Right.
Hour of Code is like a subset of what they do,
Okay.
which is probably the most hyped up thing that they do. But they
Okay,
have
is that where you are, or are you someplace else?
we're doing something they have called a 20-hour like course,
Okay.
which is a lot. It's a longer thing.
They have 3 main courses they offer right now. CS Fundamentals is a K-8 course that's theoretically over 20 hours.
Okay.
They have a middle school focused course that's brand new called CS Discoveries. It's modular. I think there are 5 units that are sort of modular units in different subject areas. Then there's a high school course which is aligned to the AP Computer Science Principles.
What was the first one that you said?
CS Fundamentals.
CS
That's the
Fundamentals.
20 hour. There's actually like 2 or 3 flavors of it if you go to their website.